NEC Article 700.20c addresses requirements for emergency systems, specifically focusing on circuit breakers that serve as feeder overcurrent devices for emergency electrical systems such as emergency lighting. The code mandates that these circuit breakers must be clearly identified and lockable in the on position. The rationale behind requiring lockable circuit breakers for emergency circuits is to guarantee their availability during a normal power outage. This lockable feature is designed to prevent accidental or unauthorized tripping of the circuit breaker, which could inadvertently disable the emergency lighting system. This is crucial because emergency lighting is intended to provide illumination during situations when the primary power source is unavailable, ensuring the safety of occupants and facilitating emergency operations. While Article 700.20c explicitly requires clear identification and lockability, it does not specifically mandate that circuit breakers for emergency circuits be red. However, the use of red circuit breakers is a common industry practice. This color coding serves as a visual aid, making them easily recognizable during an emergency. The visual distinction can be critical for quick identification and operation, especially in stressful situations where immediate action is required. Based on the NEC requirements, a circuit breaker supplying emergency lighting in a substation control building should be both lockable and preferably red. These features are essential for ensuring the availability of emergency lighting in the event of a power outage. The lockable aspect prevents unintended disconnections, while the red color enhances visibility for quick identification. If an engineer is overruling the code requirement for a lockable or red circuit breaker for an emergency circuit, it could constitute a violation of the NEC. It's important to recognize that compliance with the code is mandatory, even for municipal utilities. The NEC sets minimum safety standards, and adherence to these standards is not optional. Non-compliance with the NEC code can lead to severe consequences. Firstly, it can create safety hazards for both workers and the public. Inadequate emergency lighting can result in accidents, injuries, and even fatalities during emergencies. Secondly, non-compliance can lead to liability issues for the utility and individual engineers. If an incident occurs due to non-compliance, the responsible parties may face legal repercussions. Thirdly, potential fines and penalties can be levied by regulatory authorities for violations of the NEC. To ensure compliance with the code and to provide the necessary level of protection for the emergency lighting system, it is recommended to install a lockable and preferably red circuit breaker for the emergency lighting circuit in the substation control building. This approach aligns with the intent of the NEC to enhance safety and reliability. When interpreting the NEC, it is important to consider the definitions provided in Article 100. These definitions provide clarity and context for the terms used throughout the code. It is also important to be familiar with other relevant articles in the NEC, such as those addressing overcurrent protection, wiring methods, and grounding. Firstly, in the specific context of emergency lighting circuits, overcurrent protection is critical to safeguard the circuit and connected equipment from damage caused by excessive current flow. Circuit breakers and fuses are the two primary types of overcurrent protective devices commonly used. These devices are designed to interrupt the circuit when the current exceeds a predetermined level, preventing overheating, fires, and equipment failure. Secondly, wiring methods play a vital role in ensuring the safe and reliable operation of emergency lighting circuits. The NEC specifies approved wiring methods for different applications, taking into account factors such as voltage, current, environmental conditions, and physical protection requirements. Common wiring methods include conduit cable trays and direct burial cables. Thirdly, grounding is an essential safety measure in electrical systems, including emergency lighting circuits. Grounding provides a low impedance path for fault currents to flow back to the source, allowing overcurrent protective devices to quickly trip and energize the circuit. Proper grounding minimizes the risk of electric shock and prevents the buildup of static electricity. The specific requirements for grounding are detailed in Article 250 of the NEC. Additionally, understanding the concept of selective coordination is crucial in the design of emergency systems. Selective coordination ensures that only the overcurrent device closest to the fault will trip, while other upstream devices remain closed. This minimizes the extent of the outage and maintains power to other essential loads. Article 700.27 of the NEC addresses the requirements for selective coordination in emergency systems. Furthermore, regular testing and maintenance of emergency lighting systems are essential to ensure their proper operation. The NEC requires periodic testing of emergency lighting systems to verify their functionality and battery backup capabilities. Regular maintenance, including cleaning, inspection, and battery replacement, is also necessary to maintain the reliability of these systems. In addition to the NEC, other codes and standards may apply to emergency lighting systems, depending on the specific application and location. These may include local building codes, fire codes, and standards from organizations such as the National Fire Protection Association. It is important to consult with qualified professionals and local authorities to ensure compliance with all applicable codes and standards. Moreover, when selecting circuit breakers for emergency lighting circuits, it is important to consider several factors, including the voltage rating, current rating, interrupting rating, and type of trip unit. The voltage rating of the circuit breaker must be equal to or greater than the system voltage. The current rating of the circuit breaker must be sufficient to handle the continuous load current of the circuit. The interrupting rating of the circuit breaker must be adequate to safely interrupt the maximum available fault current at the installation location. The type of trip unit determines the response characteristics of the circuit breaker, such as instantaneous, inverse time, or adjustable settings. Lastly, consider the use of surge protective devices, or SPDs, to protect emergency lighting circuits from voltage transients and surges. SPDs are designed to limit the magnitude of voltage spikes, preventing damage to sensitive electronic components in lighting fixtures and control systems. SPDs are typically installed at the service entrance or at the individual lighting panels. In conclusion, adhering to NEC Article 700 and related requirements is essential for ensuring the safety and reliability of emergency lighting systems. Implementing lockable and preferably red circuit breakers, understanding overcurrent protection, wiring methods, grounding, selective coordination, regular testing, compliance with other relevant codes and standards, proper selection of circuit breakers, and the use of surge protective devices are all critical aspects of designing and maintaining effective emergency lighting systems. Proper implementation ensures the availability of illumination during emergencies, protecting people and property.